Oh, you're back, I see. Okay. So, physics first semester, calculus based, final exam review number 2. We are up to working with forces at this point. And so let's talk about some forces. First, weight. Um, I don't have a lot to say about weight. I always write it as mg because I think using the old w is a waste of time. And I have other things that I like to save this for, so I just do mg. Mg is weight. Okay, done. Next, the normal force. Normal force. Huge. This is a big deal. It's the force from the surface of one object onto the other object. It could be a table, it could be the ground, it could be a wall. It could be any time two things are touching, they are providing a normal force on each other. So that's why I draw this picture here pretty much every time. It used to be two kind of circles nuzzled up against each other, but for obvious reasons, I don't do that anymore. So now I have the block and the circle, and one is touching the other, and they're both pushing on each other. Okay, so the force of 1 onto 2 is equal to the force of 2 onto 1, but these things are vectors. So therefore, there's a negative sign because one's pointing in the opposite direction. So equal and opposite. So this is the epitome of Newton's third law. All right. So if the objects aren't touching, if they don't touch, then there's no normal force. But if they are touching, there's a normal force. It could be very, 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 very small, but it's still there. Okay? So that's how that rolls. Okay. So let's talk about tension. Tension is pretty simple. But we talked about tension today in class dealing with restoring forces. And so tension requires that forces are transferred through the flexible medium, like a rope or cable or whatever. And so since it's flexible, you can only pull and you can't push on it. That's fine. But it also provides restoring forces. So once that happens, then we can also do what we're going to do later, and that is send a signal down the wire or down the cable or the chain or whatever it is, belt, it doesn't matter. And we can send a signal down that wire, and we will see that later. And it has to have tension, because if it doesn't have tension, there's no restoring force. So we'll talk about that. Okay. Then we have spring forces. Hooke's law. Hooke's law has this F equals minus kx. Now, this is important. The minus sign means that our displacement x opposes our force. So if we're on one side, if we're over here with x, our force is going in this direction. If we're over here with x, then our force is going in that direction. So it always wants to put us back to equilibrium. The equilibrium position is right here. So that's what Hooke's law does. And again, that's a restoring force, and therefore can give rise to waves and other things that can transmit energy or information or whatever. Okay. Then there's gravity. We already talked about how gravity is the only thing that we're really dealing with as far as forces go of the four forces. Since we're talking about that, gravity is pretty much the only one that we're really discussing. However, the normal force is electromagnetic. Okay, so even though we know it's there, it's an electromagnetic E&M force. Okay, and not forces, it's just a force. Yeah. So, but are we going to really talk about that? Am I going to ask you anything about that? No. We're going to pretend that we don't know this, and it's just a force that's out there in the world that we just don't really know the root of or whatever, but secretly you do. Okay. So gravity. Gravity is the one thing that we're really working with technically, and so we talked earlier about how gravity is the force of gravity equals mg, right? But that's if we're at the surface of the Earth. But we're not always at the surface of the Earth. Sometimes we're out in space. I don't know. Maybe you're an astronaut on your weekends. I don't know. So Newton's universal law of gravity um, is what we have studied, and that's what we're going to be tested on. Okay, Newton's universal law of gravity. I just want to point out that this was superseded by Einstein's general theory of relativity. Okay, so this theory is way more encompassing than this law. All right, so yeah, so we've stepped forward from laws to a theory, and that seems just about correct in this world. Okay, next, friction. All right, friction is easy. All right, it's just bonds that form at the surface of two distinct objects. What are the bonds? Again, we're talking about electromagnetic bonds. All right, we've got electrons, and they're floating around their atoms and or molecules or whatever. So here we have positive, and then outside we have a whole bunch of negative stuff. But the electrons figure out ways to find their lowest energy state, and they will do it with the other object nearby. And once they've found a low energy state, well, they're happy. And they're happy to be next to each other, the two items. And they're like, oh man, I like you, you like me, all right. And so then they just sit next to each other, kind of bonded, okay? And that's just the nature of the world. Things stick together. Hardly anything slides. I guess there are some slick things out there like soap or whatever. We call soap a surfactant because the surface is freed. Okay, so whatever. But let's get back to friction. Okay, not trying to minimize friction, oil and whatnot. So we've got these bonds, and that's what friction's all about. I'm not going to give you the other bull that the book tries to sell you on. The more the objects are pressed together, the larger the friction is, because they're being pressed together means that the bond is being further enhanced. Okay, so that's why your normal force times your coefficient of friction increases your friction. If the normal force increases, your frictional force is going to increase. Okay, now these aren't vectors. All right, there's no vectors on these forces, they're just magnitudes. Okay, because if you know, the normal force is going to point up and the frictional force is going to point to the side. That's their vectors, but they are related in this relationship, okay, through the coefficient of friction. All right, so they're not vectors in this equation. These are not vectors, they're just magnitudes. All right, so there are two types. You guys know this. Kinetic and static, right? We've got mu kinetic and mu static, and we know the mu static is greater than mu kinetic, and we talked about why, and why is because when objects are not sliding, then the force of friction is more because they're wanting to be bonded more. If they're sliding, they don't have as much time to allow the electrons to find their minimal positions, and therefore the bonding is minimized. Okay, so Then there's drag. All right. So not me on Saturday night. I'm just kidding. I've never done that, but I think it would be funny. Okay, so force of drag. We've got this kappa times our velocity squared. All right. This is friction between the object and whatever the medium that it's moving through. What is that medium? It could be air. It could be water. It could be oil. I don't know the chemical thing for oil. I'm sure there's many. So this kappa is actually a breakdown of, or a conglomeration. It's a mash together of 1/2 C rho A. All right. So C rho A. For some reason, I can remember that because I remember cover your butt, cover your C rho A, and it works for me. So we have the drag coefficient, that's C, that's of the object. We have the density of the medium, that's rho, that's your density of the medium. And then we have A, which is our forward-facing area. Forward-facing means the area that is subtended as the thing is moving in this direction. So you're moving in some, I'm calling it velocity wave because so you're moving in this velocity through the medium, and I don't know, maybe it's a billboard or the front of a Mack truck. So it looks like this. This whole area is the area that I need to think about as this thing is moving forward, okay? I don't care about the rest of the truck really, all right? Now in fluid dynamics, we care about all the stuff behind, but we're not, no. You guys, people spend their whole lives doing fluid mechanics, and it's very, very difficult. And so we're gonna just keep it simple, all right? We're doing it this way, and that's it. This is as much as we are gonna see. Okay. So, but friction of any type is a force that opposes the velocity vector exactly in the opposite direction. It wants the object to slow to a stop and merge with its surroundings. Okay, so when you get a flat tire, your car's wanting to merge with its surroundings, and it's just natural. There's nothing you can, I mean, you can do stuff about it, but it's the inevitability of the world. Okay, so what about static friction? Let's talk a little bit about static. In static friction, of course, we're going to use mu static. And in this case, we've got a velocity that equals 0. We've got some box on a plane. I've labeled some coordinate systems here, and we're going to use those coordinate systems to figure out that our force in the y direction is 0, our force in the x direction is 0, the sum of all forces. So that gives us this and this, and then we can use this equation to replicate this equation, and therefore, thereby, we have mu static is equal to the tangent of our theta static, okay? And since we're static here, I can throw a little s on there, and that's our theta static. And a similar argument, I'm not going to get into it, okay? It doesn't matter. You can look at the argument, whatever, but it's going to give you the same relationship, okay? But it's tangent of theta kinetic. What does that mean? That means the whole thing has now moved, so we're at a different theta, we're at different theta kinetic, one where this box actually will slide with a v, okay? So what is that v? That's a terminal velocity. because there's no acceleration, it's constant, and the force of friction is acting backward, and we've got our mg sine theta acting forward. Okay, and they're balanced, no acceleration, but yet moving. Okay, that's what happens when you get to the right theta. That'll happen for you. Okay, maybe you gotta nudge the thing a little bit. You gotta nudge your box just a little bit, and then it'll slide on down. Okay. All right, so in the kinetic situation, this is true. So we have our terminal velocity and no acceleration, and v is constant. I already went through that, so we're good there. All right. So now forces. Forces all have to follow Newton's 3 laws. They basically, all this stuff is Newton's 3 laws, and they come from this. So I should have probably led with this, but I'm going from those forces to this. Just, I don't know, go with it. So mass is equal to inertia. This is huge. This is critical. Okay, you got to know this. All bodies have mass, and therefore they want to stay inertial. They want to stay still, or they want to keep a constant velocity. But if a force makes them move, that's the whole point. That's why they call it a force. You are being forced to do something. To do something. Stop making me try and do stuff. I don't want to record videos. Okay, so forced to do something. This is a force, and the force is making them move. Okay? Great. Otherwise, they would stay still. The moment, number 2, the movement is an acceleration, of course, if there's no friction present. So we don't want friction to be present. In that case, we can call it an acceleration. And if it is present, then we'll get some movement, but no outright acceleration, whatever. But let's say there's no friction. So in that case, no matter what happens, if we apply a force on an object that has an inertia, we apply a force, we're going to get an acceleration. Okay? The most common way to see this is right here. F equals ma. This is Newton's second law. There's no way around it. It's really, really solid. So the third law, all forces from one body onto another body, I should put body here, onto another body, are reciprocally equal and opposite. All right, so the example of the box on a table, there's a normal force of the table pushing on the box. There's a mg of the box pushing down on the table. And the two things are equal and they're opposite. Okay, so that means that F12 is equal to F21. They just happen to be in magnitude. They happen to be pointing in opposite directions. Okay, that's where the negative sign comes in. Okay, Newton's third law. And it works, it always works. And we talked about why things can still move, and that is because some things have less friction than other things. And you use the friction for your own benefit, and then you can make other things move. Okay, so just think about that for a little bit if you weren't there that day when we talked about it. Using F equals ma, we can sum up all the forces on an object. Okay, so there may be many forces, and we can do that. And we can take all of those force vectors, and we can add them all together, and we can come up with this thing in the end is a vector if we take the mass times that, we'll have all of the forces combined. That's great. A net is the object's acceleration due to all of those acting forces. Okay? If you take one out, A net's going to change. So typically, we call A net just A. Okay? A or A vector, whatever. And then once we know A, we can start doing other things. We can start getting our velocity. We can start getting our position, right? Our radius position, our radial position, or our X, Y, and Z, or whatever. So how do we do that? We have our A equals dv dt. Now this is instantaneous acceleration. And that's A of t. Actually, I want to write A of t. That leads us to V of t. If we take the derivative of A of t with respect to t, then we're going to get our V of t. And then we can get the speed from that V of t. We put V of t in here, and we can get our speed. How do we get that? I told you in the previous video, we just do the dot product and take the square root, okay? And that's going to give us our absolute value, and that gives us our speed without any vector associated. Then we can get V of t if we take the derivative of x with respect to t. So that means that once we have V of t, we can get x of t by doing the integral. Okay, so these work both ways. Specifically, since we have A to start with, we can then get V. Once we have V, we can get x. So you guys know the drill. All right. So that leads us to positions. And if we're here, we've got some x final minus x initial, right? Well, delta anything is the final thing minus the initial thing, okay? So that's how that works. So if you have delta V, if you have delta A, if you have delta kinetic energy, it doesn't matter. The final minus the initial, okay? So do that. Now, this all works in reverse, and we've done this before 100 times too, so you should be familiar with that. And those are all the instantaneous versions. But if we do averages, then we can say, we can start with, okay, I've got some delta x, and we move delta x in a certain amount of delta time. And yeah, so then just off to the side, I neglected to deal with time here for a second. Time, where do I have my thing written down? I got something written down for time. Yeah, time is something we can measure in a way. It's the increase in entropy, which has to do with friction, by the way. And it gets complicated. But entropy is always increasing, and therefore time is always increasing. That's why you can't go back in time. So this is the link. All right. There may be a question on the test about that time. I don't know. I just want you to be aware of it. Okay, so let's move on. So we've got our delta x over delta t. All right. And a lot of the times t equals 0, so delta t really is equal to t, and that's nice. And our A average is equal to delta V over delta T. So we can start looking at these equations, and if we write out delta X, there's our V average, and there's delta T. That leads us to our X final equals X initial plus our V average times time. The same thing goes for the average equation. For the acceleration average, and that's going to give us this equation, okay? And if you really want the average, you can take the final, add it to the initial velocity, and then you get your average velocity. And I'm not deriving them or showing how they come about, but you guys, if you were to do the integrals, you would get these things. And a little rearranging of time, and we will get that as well. So all of these equations are really important, and they are, fundamental, we'll say. All right, so all of this leads us to an acceleration, a centripetal acceleration. When some object is moving in a circle, the key to take away from centripetal acceleration is this right here. I should have capitalized every single letter. I should shout from the rooftops. The rooftops. Then the net force is the centripetal force. So when you sum up all the forces that are acting on this guy right here, this object right there, you're acting on that with a whole bunch of forces. It doesn't matter how many. You're gonna get the centripetal force. That's the net thing, because it's traveling in a circle. It wouldn't travel in a circle if it didn't have the net force acting on it. Okay? So that means your force centripetal is equal to an ma. So there's our mass of the object times some acceleration that's centripetal. And we've summed up all the forces to get that. We discussed in class, and I showed you over and over, how our centripetal acceleration is equal to this omega squared times r, or v squared over r. Now, there are many, many reasons to use different ones. And if it turns out you're doing a rotational situation where you need omega squared, this is the one to use, right? If you're doing a linear situation where it's 1/2 mv squared, then this is a better way to go. Typically, however, this one is the best, okay? So I emphasize, if you can, use r omega squared, okay? If you can do it, if it's not hard to go out of your way. If it is, then you're probably better off with this, okay? But if you have to go out of your way to do v squared over r, then just forget it, drop it, okay? All right. So now we have two different types of uniform circular motion or non-uniform circular motion. Two different types. When v and omega are constant, then that means that your tangential acceleration is 0, okay? So let's look at a picture. Okay, so here's our tangential acceleration, and here's our centripetal acceleration. Which way does it point, by the way? Centripetal acceleration always points towards the center. Always. Doesn't matter where it is, it's going to point towards the center. That's why sometimes we make that the positive and out as the negative, just so that we know that's what we've got in the end. we've got a positive in the end. It doesn't matter if you end up with a negative because you did it the other way. That's fine too. Don't worry about it. Okay, where was I? Non-uniform circular motion, our velocity is not constant, our omega is not constant, and therefore we have a tangential acceleration. So if you have a tangential acceleration and you have another acceleration towards the center, in order to get the net, what is the net? The net is pointing here. Okay, it's the combination of both the tangential and the centripetal. So to get your magnitude, you do this. And then if you want to get that angle, then theta A is going to be equal to the arctangent. And what do we want? Do we want AC to be in the x direction? Yeah, let's do AC. So then we'd say AT over AC, and that would be with respect to the radial, radial direction. So AT equals this. AC equals this. Now, if AT is changing, then that means these guys are changing, right? If those guys are changing, then you have to do it moment by moment, right? You have to know exactly at what point you're dealing with, and then you can work with this problem. Okay. So let's recap a little bit. We've got our x equals vt, our 1/2 v final plus v initial is our v average. We've got this guy happening, we've got that, and then we've got the cool one that gets used quite often. This relates to both energy and it is positional without time. So without time. So that's a very useful equation, so don't neglect it. Pops up so many places. Okay, so you can take all of those things and they can all be transmitted to a vertical situation where you would look at turning your x to a y, and then your acceleration is now a g. Or you can do it rotationally. In that case, we end up with our x going to theta, v goes to omega, a goes to alpha, and of course you have to keep in mind your centripetal acceleration. And all of those same equations are there. I'm not going to rewrite them because you guys can do that, but it's the exact same equations. So let's talk a little bit about projectile motion. If you want to get the r vector, then you want this vector, okay? So you need to know this is your x as a function of t, and this is your y as a function of t. All right? So we've got that. All right? Now, we've got those two things, and if I want, I can get the magnitude of it simply by squaring that and squaring that, and then taking the square root of them added together. I get the magnitude. Or I can get theta r like this. Now, you have to be able to do a little algebra because chances of me asking you how to do this one direction only is not great, right? The other thing is, a lot of the times in order to work backwards or forwards, a lot of the times you need to know what V naught is, and you need to know what theta V naught is, right? That theta V naught. So if you know those things, you can then easily come up with V naught x and V naught y. Those are important. And from there, you can go on and do a whole bunch of stuff. Now, I don't know. Here we go. If we know V naught x times t is equal to 52 meters, and we know that t equals 4.8 seconds, and we know that V naught is equal to 60 meters per second, can we find theta V naught? Can we find y of t at that point? How high is it off the ground? Can we find v of t? Can we find theta of v? If you can do those things, you're doing great. Okay. Also, if you can't, then it might be my fault because I may not have given you enough information. But I think all the information you need is there, and you can track down the rest of it with those things. And I also hope that the numbers that I gave are legit numbers. I think it'll work out, but it might be a crazy. It might not be as the parabola that you were hoping for. These are not the droids you're looking for. So vt, our velocity as a function of time, is the velocity at any point along the path. And this is also true, okay? So let's look at what I'm talking about. I'm talking about some velocity here, okay, at any point along the path, okay? So if you need those equations, they're there. And then usually the problems that were done in the homework all revolved around these things here. Not all of them, but a lot of them. So I used the heck out of these equations when I was solving problems of this type. I was using these equations left, right, and center, and it's very helpful. In fact, extremely helpful. Yeah. So I'm going to stop this video now because we've got some statics and dynamics to talk about next, and torque and whatnot. So good job hanging in there.